So we're going to be moving on to the the redox reaction part of this module, which is essentially we're going to go over how to balance redox reactions and just what they are. So I know that you guys probably brushed redox reactions while you were in Chem 1, but it didn't go in as deep as we're going to, because yeah, there's a special way of balancing redox equations that kind of take a while, but they're my favorite thing to do, which I know you guys might think I'm insane for it once we do it, but I like it. It's a nice repetitive pattern. But anyway, so redox reactions deal with the movement of electrons. Movement of electrons. As in, it's just these compounds in the reaction shift electrons, like some of them gain them and some of them lose them just to make the reaction work. And with redox reactions, you have your oxidation, and your reduction, which essentially your oxidation is a loss of electrons, and your reduction is gain of electrons. Which I know it's kind of backwards, but like it's called a reduction because when you're adding electrons to something, you're actually making them more negative. So you're reducing the charge. Like, yeah, I know it's weird because you're like, reduction shouldn't be gain, but it is. And a like simple way of remembering that oxidation is loss and reduction is gain is by the mnemonic of oil rig, which just means oxidation is loss and reduction is gain of electrons, like, you know. But yeah, if you guys ever forget what oxidation is and what reduction is, as long as you remember oil rig, it should be fine, just because the L stands for loss and the G stands for gain. So yeah, this is just a fun mnemonic to remember it by. And then, so something funky about nomenclature in redox reactions is that you have a thing known as the reducing agent, and another thing known as the oxidizing agent. Ooh, I should have done these in backwards color so that they still coordinated. But, okay. So your reducing agent is essentially the thing being oxidized, and your oxidation agent is the thing being reduced, which, yeah, it's just the opposite of what's happening. So essentially why it's known as a reducing agent or the oxidation agent is because the thing being oxidized is causing the other compound to be reduced. So therefore it's your reducing agent because it's the cause of the reduction. And same thing for the oxidizing agent, is that your thing being reduced is causing the other thing to oxidize. Therefore, it's causing the oxidation, so it's the oxidation agent. So yeah, if you guys just see the word agent after reducing or oxidizing, just think the opposite. So if I were to add, like, if they just ask you what is a reducing agent, it's the thing being oxidized, it's the opposite, and vice versa. So right, the next thing we're going to move on to is balancing redox reactions, which it is different from how we normally balance equations, because when we normally balance equations, we just kind of see, okay, we need this many moles on one side, so we have this many moles on one side, so we need them on the other. We just put numbers in front of it and it's cool. With redox reactions, you can't do that because you have a transfer of electrons happening. And while, yeah, your elements may be equal to each other if we just put numbers in front of it, the charges aren't going to be equal, like on your product and reactant side, and that's what we care about with redox reactions. So yeah, so this is going to be balancing using the half reaction method. Half reaction method. So then a mnemonic, oh my god, I forgot the word for that, for half reaction method of just how you know what you're supposed to do is known as MOHI, and this is after you split them up. So M stands for moles of compounds, not compounds, elements that are not hydrogen or oxygen. And then O stands for oxygen, H stands for hydrogen, and E stands for electrons, which we'll get into what each of these mean like when we do an example, and that's exactly what we're going to do. So let's take the redox reaction Cr2O7 minus 2 aqueous plus nitrous acid aqueous yields chromium ion aqueous plus the nitrate ion aqueous. So the first thing we're going to do is we're going to solve for oxidation numbers of things, just so that we can see what is being reduced and what's being oxidized. Like you can kind of split these up by half reactions just by, okay, this has chromium and this has nitrogen. These are two half reactions. But in case they ask you like what's being reduced and what's being oxidized, which I'm pretty sure they will, let's do it. So, okay, chromium, easy over here on this side, it's just +3 because your oxidation number has to equal your overall charge, and there's nothing in front of it or it mixed with anything, so it has to be +3. And then looking at nitrate, we know that oxygen has to have a -2 charge, and since there's 3 of them, it's an overall charge of -6, and we have a -1 charge overall, so we have to solve for what plus -6 gives me -1, which would be +5. So then onto the reactant side, with nitrous acid, again, we know that oxygen is a -2, and there's 2 of them, so it's -4, and then hydrogen is always +1, and our overall charge is 0 because it doesn't give me a plus or minus next to it, so 0. So 1 plus 4 gives me -3, so -3 plus what gives me 0, and it's a +3 on our nitrogen. So then with chromium, again, oxygen, we have a -2 times 7 gives me -14. And okay, so this one's a little funky, so I'm going to write out the whole equation. So we have -2 is equal to -14 plus 2x, which is going to be a chromium, because we have 2 chromiums. So then algebraically we have 12 is equal to 2x, so x is equal to +6. So chromium has an overall charge of +12, but each one is +6, which that's the oxidation number of chromium. It's +6. So then now looking at it, we're just going to look at our nitrogens because our oxygens are just, yeah, we know the oxidation numbers of them normally, so we usually look at whatever is not an oxygen or a hydrogen to figure out what's being reduced or oxidized most of the time. So then if we're going with chromium, from a +12 to a +3, so we're getting less positive, right? Like we're going from 12 to 3, that's a decrease. And the way to decrease something is to add electrons to it, which means that we're gaining electrons because we're becoming less positive. So if we're gaining electrons, we're a reduction, because if you guys remember oil rig, reduction is gain. So these two right here, ooh, that came out very crooked, but okay, are the read part of our redox reaction. So then that means that the other thing has to be the ox, which is the oxidation, but even if you look at it, you're going from a +3 to a +5, and that means that you're losing more electrons because you're becoming more positive, which means that you're losing the negative part of you. So, yeah. So then this part, these pairs right here, are our red part. So then in the question, if I were to ask you, oh my god, not the red part, the oxidation part, my bad. Oxidation, oof. But yeah, in a question, if I were to ask you what's our oxidizing agent, you would say that it's our CR2O7. And if I were to ask you for the reducing agent, you would say HNO2 or nitrous acid. So that's just kind of the how to split them up part. Now we're going to get into the actual balancing, which, okay. Wait, time out. I need to still show the Mohi part. My bad. There we go. So then we're going to break apart our things into our reduction and oxidation half cells, which is going to be CR2O7 minus 2 yields CR3 plus, and then we're going to have HNO2 yields NO3 minus. Cool. So then the first part of this tells us, well, the first part in Mohi tells us the moles of elements, not hydrogen or oxygen, need to be balanced, is essentially what this means. So we're balancing moles of elements that aren't hydrogen or oxygen. And in the case of our reduction, we have 2 chromiums on this side and just 1 on this side. So we put a 2 in front of it. And then in the case of our reduction, we only have 1 element that isn't hydrogen or oxygen, and that's the nitrogen. And there's only 1 on each side, so we don't have to balance it. We just leave it. So then that's the M part done. So then next we move on to balancing the oxygens. And as you guys can see in our reduction part, we have 7 oxygens in the reactant side and none on the product side. So to even that out, we add water. So we're going to add 7 waters just because water only carries 1 oxygen and we need 7 of them. So 7 H2Os. And now for our oxidation, we have 3 oxygens on the product side and 2 on the reactant side. So we only add 1 water to turn it into 3 oxygens. So then that's it for the oxygen. So then now we have to balance hydrogens because adding the water onto the product side gave us hydrogens and we don't have hydrogens on the reactant side. So we need to add however many hydrogens that there is. So 7 times 2 gives us 14. And to add hydrogens, we just add the hydrogen ion. So we have 14 H pluses now on the reactant side. And now for this one, we have 3 hydrogens on the reactant side and none on the products. So we add 3 H pluses and we get the 3 H's from the 2 from the water and the 1 from the nitrous acid. So then that's it for hydrogens. So now we have to balance the electrons, which essentially means that your overall charge on the product side needs to be equal to your overall charge on the reactant side for both of your 2 equations. So overall we have a 14 charge on our 14 hydrogens and a -2 charge on our CR2O7, so that our overall charge is +12. And now on this side, our water is 0 because it's in its elemental state, like it's stable, and our chromium is going to be +6 because we have 2 + 3 charges. So then 12 to 6. We change this by adding electrons, which means we're adding negatives, which means we're going to make it less positive. So we want to go from 12 to 6 by subtracting 6 essentially. So we're going to add 6 electrons because electrons are negative. So we're subtracting 6 from 12. So you can just think of it that way, like how much do I have to subtract from one side to get to the other, and that's where I would put my electrons, to the side we're subtracting from. So then let's look at our other thing, at our oxidation half. So on this side, we have an overall charge of 0 on our reactants because both of them are in their stable states. So we have an overall charge of 0. And now on our product side, sorry, I'm like wearing a jacket, I don't know why. But on our product side, we have a -1 charge here and a +3 charge with the hydrogens. So we have an overall charge of +2. So, like I said, by adding electrons, we're subtracting. So +2 electrons to get this is essentially +2 minus 2 to give me the 0, so that we have our overall charge of 0. Okay, so then that's it for the electron part of this. So then finally our final steps are going to be combining our two half reactions again. And before we can combine our half reactions, we have to make sure that our electrons are the same value. So if you guys see on our reduction side, we have 6 electrons, whereas over here we have 2 electrons. So to fix this, we're basically going to multiply it all by 3, because to get 2 to 6, we multiply by 3, right? So we just rewrite everything so that we have 3H2O plus 3HNO2 yields 3NO3 plus 9 H pluses, that's a 3 I promise, plus 6 electrons. So that's going to be our final oxidation half, and this is our final reduction half, and now we're going to combine them again to get one big equation like this one up here. So then I'm going to rewrite it over here as 3H2O plus 3HNO2 oh my god, yeah, yields 3NO3 minus plus 9 H plus 6 electrons. So then essentially you're going to have your like terms cancel, so your 6 electrons are going to cancel because they're on opposite sides of the equation. And then, so we have 14 H's here and 9 H's here. So these 9 H's are going to be gone, and this 14 is going to turn into a 5 because it's 14 minus 9, right? And then another thing we can cancel are our waters. So we have 3 waters on this side and 7 on this side. So this the 7 is going to turn into a 3. So then we do our final combination now with everything being changed. So we have 5 H pluses plus 3 HNO2 plus Cr2O7 minus 2 yields 3 NO3 minus plus 2 Cr3 plus 3 H2O, and then we check our work by essentially doing our charges overall. So this is 0 plus 5 minus 2, so that we have a plus 3 overall, and then minus 3 plus 6, 0, negative 3 overall. So then we're done balancing. And oof, I need to plug in my computer. But okay, so something that you guys need to keep in mind is that this balancing, the steps that we've done, is known as acidic conditions. Acidic conditions. Okay, so this is bad videos, but I'm gonna get my charger so my laptop doesn't die before I finish explaining. So sorry for leaving you guys for like 3 seconds because I really don't want this to die while I'm in the middle of an explanation. Okay. There we go. I'm back. I'm so sorry about that. But, okay. So then, yeah, like I said, this is in acidic conditions. So, we don't just have acidic conditions, we have basic conditions, which essentially basic conditions, you follow all the steps that we did for acidic conditions, which was the separate them into your two halves, balance the moles of things that aren't hydrogen or oxygen, balance the oxygens by adding water, balance hydrogens by adding H ions, balance electrons, and then combine everything so that you're left with your one final long equation, right? And this would be the end in acidic conditions. But if we're going into basic conditions, so I'm going to rewrite the same formula just because we already went through all the steps. So we're going to have 5H plus 3HNO2 plus Cr2O7 yields 3NO3 minus plus 2Cr3 plus 3H2O. And what you do in basic condition is to, on either side of the equation, you add the same amount of hydrogens, you add the same amount of hydroxides as hydrogens. So you would add 5 OHs to this side and 5 OHs to the other side because we have to do the same thing on both sides. So then because you added these OHs and you have the same amount of H plus OH gives me water. So then now my equation is going to have a 5 H2Os plus 3 HNO2 plus Cr2O7 2 minus yields to 3NO3 plus 2 chromate plus 3H2O plus 5OH minus. So now we can do the same thing that we did before, where it's essentially you cancel out things on opposite sides of the equation. So I have 5 waters here and 3 waters here. So then what I do is that this 3 water is going to be gone and this 5 is going to turn into a 2. So that our final equation in acidic condition, in basic conditions, is 2H2O plus 3HNO2 plus Cr2O7 2 minus yields 3NO3 plus 2 Cr3 plus 5OH minus. And then now we double check our, oh my god, what's the word I'm looking for? We double check our charges again. Yeah, I know. So let me do this in a different color just so that we can see it. So our H2O is 0, 3HNO2, 0, chromium, minus 2. 3 NO3s is minus 3, 2 of our chromiums are plus 6, and then 5 OHs are minus 5. So if we were to add all of these together, we would end up with a negative 2. Our charges are the same overall on both our reactant and product side. So we're done balancing. And like I said, this adding OHs is just if the problem tells you in basic conditions. You don't have to do it if it's acidic conditions. In acidic conditions, you're done after doing the MOHI. With basic conditions, you add the OH, which, yeah, I know this is a long process to do, but it's not that bad in my opinion. Like, I love doing redox balancing. Yeah, I know, it's kind of crazy because it's so long. But once you get into the flow of it and you just follow the MOHI going through it, it gets pretty simple the more you do it. So yeah, that's it for the redox reactions.